I'm Ruben Iglesias, and in this presentation, we'll cover the updates on the precision time protocol that are available with the AOS-CX 10.11 release. We'll start with some acronyms here. PTP, we'll use that for precision time protocol. E2E means end-to-end delay. P2P, peer-to-peer delay. And then for the different clock types, GSC is the grand source clock or the main reference clock. And then BC is our boundary clock, TC our transparent clock, and OC the ordinary clock, or we can call that in general the client. And then VSF is our virtual switching framework or stacking technology for the 6300 switches and 6200 switches. And COPP is our control plane policy feature. So let's get started with PTP, peer-to-peer delay. We'll take a look at a short overview, what this means. We'll define it, then we'll go through details and caveats, then some use cases, finally configuration, troubleshooting, and a short demo. So we'll start with a short definition or a short introduction to peer-to-peer delay. So PTP needs or uses a delay, the calculation of the delay to the delay between the source and the sink, so the source and the client of the PTP interaction, to adjust the offset that will represent the deviation that the sync clocks is experiencing in reference to the source clock. So to measure the delay, the sync sends a packet that is a delay request to the source or upstream, and it will receive a delay response, and it will take the times of the delay response, and it will use that to calculate or to add that to the calculation of the offset. When we have between the source and the sink one or more transparent clocks, then if this transparent clock uses that characteristic of being transparent, it will forward the delay request all the way up to the source, and it will be the source that will respond to each delay request from every sink connected to every transparent clock that is in downstream from that source. So there's another option, it is to do this in steps. Instead of going end to end, we'll do this peer-to-peer. And of course, it's called peer-to-peer delay. So the transparent clock intermediates in that transaction. So it will send upstream its own peer delay request and will get its peer delay response. And then it will use that data and also the delay within the transparent clock itself, that switch between the ingress and the egress, and it will add all of that, and it will use that to send the peer delay response to the actual request from the sink or the client. So in this case, we have several steps of delay requests. And of course, you see that here, the names are slightly different. In the second case, we call it peer delay and peer delay response. So that is because the message code is different from one or the other. So the transparent clock knows how to handle them. Having said all of this, this second delay mechanism is the one that we are implementing. End-to-end delay, on the other hand, has been available since AOS-CX 10.8 throughout 10.9 and all the way to today. So today you have both options. let's get into some details, and finally, we'll check also some caveats. Let's review a little bit of how the PTP synchronization process works. So you see up here that we have this offset formula, and we'll go through the details of that and how the mechanism provides all this information necessary to calculate the offset. Again, the offset is the deviation of the sync's clock with respect to the source. So it is the amount of adjustment that will need to be made in each synchronization cycle. So, and by the way, T2, T1 are different timestamps, and MPD means mean path delay. And you see that MPD is related to the topic that we're covering. So you'll see that we will focus on that in particular for the analysis that we will do from now on. So let's review the mechanism itself. The source starts by sending a synchronization packet called sync. Do not confuse that with the word sync that we use to describe the client device here. And that synchronization packet is transmitted by the source at a time called T1, and it is received by the sync at a time known as T2. And here there are two options. The timestamp containing T1 could be sent directly on the sync package, or if we are using a two-step mechanism, it will be sent in a follow-up packet. Using a two-step provides a slightly more precise mechanism because the follow-up contains the timestamp of the actual transmission of the sync packet. But if you transport that timestamp inside the sync packet itself, then you had to predict the exact time when that transmission is going to actually happen. So the follow-up is a lot more precise than sending that timestamp in the sync packet. So now the sync knows, or the client knows, the T2 and T1. So it knows the difference between when the sync packet was transmitted and when it was received. So it has the first part of the formula for the offset. Now, and that's how a very simple time synchronization protocol could work. But PTP goes further and adds the mean path delay to the calculation to provide a more precise mechanism and a more precise calculation. So, in general, and we'll see then when we get back to see each one of the delay mechanisms, the sync will send a delay request upstream, and it will send it at a time 3. It will be received at time 4, and the delay response will bring the T4 timestamp, and so the sync will know when these two times happened, or these two events happened, and then those numbers will be used to calculate the second delay. So we will have two delays here to compute, and the first delay is T2 minus T1, and then the second delay is the delay of the delay request itself. So it is the difference between T4 and T3. So now the mean path delay is going to be the average between those two delays. So it's basically the sum of D1 plus T2 divided by 2. So that's the average. So that is the way that, or the generic algorithm or process for PTP clock synchronization. Now, we will focus on the delay request and responses here, and we'll take a look at that part of the process. So when you have a transparent clock in between the source and the sync, the transparent clock is neither a sink nor a source, so it does not have the capacity to timestamp the transmission and reception of those packets. However, it is intelligent enough and it has the capacity to add to the synchronization packet a timestamp that is called the resident time. So that would provide an immediate correction to that. Remember the T2 minus T1 or the D1 delay. So the first part of the delay for the synchronization packet. So that timestamp will allow us to calculate that delay more precisely. So in end-to-end delay, we use the resident time for that calculation. Now, this is how the mechanism would look like if we have end-to-end delay mechanism and we try to go at scale. You start adding more transparent clocks, more ordinary clocks, and you go to a large number. So the idea here is that the transaction, the delay mechanism, goes all the way from the ordinary clocks across the transparent clocks and to the boundary clock. However, because PTP is processed on the CPU in the control plane and not by the ASIC itself, all of these transactions hit the CPU of your switch, of your boundary clock switch, for example, your 8360 or some of the new models of the 6300s. So as you add more ordinary clocks, you will start impacting that CPU and the path between the ASIC and the CPU. If you look at the path of that between the ASIC and the CPU of our boundary clock, you can take a look at what's going on there by looking at the COPP statistics for PTP in particular. And you might find that as you add more and more ordinary clocks, you may have here a number of packet drops that is not zero anymore. So you start dropping traffic because the bandwidth that you have allocated and the priority that you have for the traffic, the PTP traffic going up from the ASIC to the CPU is not enough. So packets are being dropped. Now you could think that there's an easy solution for that, and it's to either change the priority or increase the rate. So moving from 1,000 packets per second to, let's say, 5,000. The problem with that is that you might start impacting other types of traffic. So other classes of traffic that go, that use that pipe between the ASIC and the CPU, like, for example, OSPF and other protocols, right? So you have to be very careful on manipulating the COPP parameters. So to prevent having to get into that, there's another option. And the other option is to reduce the number of requests and responses, delayed requests and responses that reach the boundary clock as part of that, reach that CPU. So that is where the peer-to-peer delay mechanism comes into play. Now, the only devices sending delay requests to the boundary clock are the transparent clocks. So now you may have hundreds of ordinary clocks, but just a few tens of transparent clocks. So with that configuration, you are saving the CPU of your boundary clock, and that would make the whole process a lot easier. So you're now dividing and conquering. Again, notice that the peer delay requests and responses have the word peer in front, and that's because those PTP messages are slightly different from the end-to-end delay requests and response messages. Now, as we said, the mechanism means that the delay requests from sinks are processed directly by the TCs, and only the TC send delay requests to the source, and the TC's delay response and response follow-ups to the sink include the sum of both delays plus the resident time. One thing that needs to be taken into account is that if you're using a two-step mechanism for the whole PTP deployment, then these interactions that we're looking at here are actually a set of 3 packets each. So we have a peer delay request, then we have a response, and then we have a peer delay response follow-up. The follow-up is the message that actually has the timestamp for representing the delay. So that is when we apply a two-step mechanism to the whole PTP deployment. Now, we said, and based on the examples that I was showing here, you might think that the most important use case is very large deployments where we have many transparent clocks per boundary clock, and of course, an extremely large number of ordinary clocks. And you may never reach that point in many PTP deployments, so end-to-end delay might work very well for most cases. However, in the future, we're working on adding new PTP profiles and new implementations of the precision time protocol for different industries. And we'll see that in many cases, those profiles force you to use peer-to-peer delay and will not support end-to-end delay mechanisms. So when we get to that point in future AOS-CX releases, you will see that we had to release the peer-to-peer delay mechanism first, even and have that available even in the case of smaller deployments. Some considerations and caveats here in terms of VSF. Peer-to-peer delay is not supported with VSF. And that applies both to boundary and transparent clock modes. And so if you are deploying VSF, the recommendation today is to deploy end-to-end delay. Also, another important detail here is that the peer-to-peer delay mode requires that all the devices in the PTP path between the grant source clock and the ordinary clocks are all PTP capable. What does that mean? That you either have transparent clocks all the way, or you have a combination of transparent and boundary clocks, but you do not have between, let's say, a boundary clock and an ordinary clock, instead of a transparent clock that you deploy there, a switch that does not support PTP, because that will create some issues with the calculation of the offset, and will not take into account the delay inside the switch, that non-PTP switch. So that's the first thing. And of course, we say here peer-to-peer, but by the way, I would make the same consideration for end-to-end delay. Now because you have the 8360s and some 6300s as boundary clock mode capable, and you have all the 8360s and all the 6300s also capable of being a transparent clock. It's not necessary to use non-PTP switches in that path. You can have them in other parts of the network, but not on the PTP path. Now, the other thing that is very important, and this is specific to peer-to-peer, and it is you should not have more than one client on a certain link to, or put it this way, on a port on the transparent clock. So the transparent clock should be connected one-to-one to each one of the ordinary clocks for the clients. And that is has to do with the way the transparent clock handles the calculation of the delays. So, and that also translates in not being able to deploy non-PTP devices between the transparent clock and the end devices. So some details on configuration and troubleshooting. There's not much here. The configuration, if you know how to configure end-to-end delay, changing that for peer-to-peer delay is extremely simple. And here's how it looks like. So as we like to say, it is half a command. So you go to the profile. In this case, I'm using the default profile, but it could be any. And then you go, remember, some profiles will force you to go to peer-to-peer, future profiles, and then you enable the profile. In this case, I'm using a two-step mechanism, and I'm on the left, I have a boundary clock configured as peer-to-peer, and then on the right, I have the transparent clock with a peer-to-peer delay mechanism also running. So as you can see, there's no secret here. It's a very simple configuration. And for the show commands that will help us eventually in troubleshooting, you have the show PTP clock will show you now the delay mechanism, now that that's pertinent and applicable. And then also the show PTP interface will show the delay mechanism on all the interfaces that have PTP. So that is something that you might want to track, and you know, this will help you to make sure that you have a consistent delay mechanism end to end. So I'm not saying end to end as the delay mechanism. I'm saying from the grand source clock all the way to the ordinary clocks that you're consistent. You either use end to end or peer to peer. Now, some troubleshooting, these steps are almost the same that we used in the past with end-to-end. The only important additional step here is to make sure that we have a consistent deployment of the delay mechanism, that we have either peer-to-peer and in all steps, and or end-to-end on every step. Now, I've added also here a verified domain ID consistency, and that is because some of the profiles do not use the 0 as the default domain ID. There is at least one profile that has a domain ID of 128 as the default. So you have to make sure that you check what is the default domain ID for your profile, and then that you configure that consistently across your whole PTP network. The rest of these verification steps and troubleshooting steps are the same that we had in the past. So now a short demo. The configuration we have for the demo is, again, very simple because peer-to-peer delay is only slightly different in the configuration and the deployment from the mechanisms that we have been looking at before. So this is just a slight difference. So we have one port here as the grand source connected to a boundary clock that in this case is an 8360 switch. And then that is a layer 3 link between the two. And then we have a layer 2 path between the boundary clock and a single ordinary clock on the Ixia device that is on VLAN 240, but in between the boundary clock and the ordinary clock, we have a transparent clock that is a 6300M switch. Now, these are the port numbers that we're using. Remember that because this is a layer 2 path for PTP, we need to specify the VLAN ID that will be used to transport PTP messages. So this is the topology that we have. Let's take a look at the actual configuration. So here we are looking at the boundary clock on the left. So run PTP. And you see the profile here at the top. The only difference with previous configurations is the peer-to-peer here. Also notice that we're using 2 steps, and that will be reflected in the peer-to-peer delay mechanism by the addition of a follow-up message to the peer delay response. So some other details, as we said, the PTP VLAN, this is the downlink to the transparent clock, port 1. And we enable PTP, we specify the VLAN, and also remember we introduced the clock source only mode in 10.10. So I'm taking advantage of that here. So this port never becomes a sync and will always be in clock mode, in source clock mode. So also the other interface, this is the uplink connected to the Ixia device. As you can see, it's a routed port. It only has PTP enable. And as you can see, we don't need here to use multicast forwarding because the transparent clock is working in layer 2, and we're extending the PTP VLAN all the way to the ordinary clock. So let's take a look at the same thing. So run PTP on the transparent clock. Now this is a lot simpler. We have the peer-to-peer transparent clock here. And then again, we extend the VLAN 240. We use that to transport PTP, both inbound and outbound. So on both upstream and downstream. And that's it. Notice that as we said here, port 1 is the one looking at the ordinary clock. And so there's no need to do anything else here. One thing that you might remember from previous demos is that if instead of having here this interface 25 connected to interface 1 on the boundary clock, we had a link aggregation group, we would have to specify what the primary PTP port, as you know, the port member or the member interface of that link aggregation group would be. You would have a primary and a secondary port for PTP. Plus, if that's a layer 2 link aggregation group, then you would specify also the VLAN, just like here. So this is all from this point of view. The configuration point of view is pretty simple. So let's get started with the demo itself to see this in action. So here I'm starting the grand source clock, and I can, so it's now started. The PTP state means that it has been elected as the grandmaster. The other option is if we had 2 of them, one would be the master and the other one would be in standby mode, so it wouldn't show as up, and it would be there ready to take the role of the grandmaster if this link goes down. But in this case, we have a single one because we've demoed that in the past a couple of times. So show PTP parent, and this is showing me that the parent clock is that port on the Ixia. And if I go to look at this MAC address, it will show me that it's exactly that port. So that is, so here's the offset, here's the phase change rate, etc. So this is working fine. You see that the grant source clock here, it's showing me the quality of that grant source clock. It has a class of 6, an accuracy of 35, and an offset of 0 because it's the grant source. So let's take a look at the boundary clock itself, and let's compare here. So remember the quality of the grant source clock. So the class was 6. Let's take just that one, and let's see the clock quality of our switch. It says that it's 248, so the class. And when we had an accuracy of 35, here we have an accuracy of 49, etc. So we see that the grant source clock is better quality than the boundary clock, which makes sense. This is why we have a hierarchy. Now we also see that here's the offset that we're measuring. And of course, this will change every time we look at the clock. You see here, and we can do that again. And you see that it varies slightly. And we can see that also in the statistics here. So port 4 is the one that is the source. And we'll see here that we have all these messages. And here's where we have all the details. Now, if we go to PTP drill down, and we see the sessions that are up, and we say refresh statistics, we will see that the only one that we have up is the master, what we call the grant source. And here we have that the maximum offset that we have seen is 0, etc. And that's because we are looking at this from the source, so there's no offset. But here we can see also the delay. And so now let's start one of the ordinary clocks. Only one. Remember that we need to have a one-to-one relationship between ordinary clocks and ports on the transparent clock. So this just came up. It became a sync. We don't use the word slave. And we go back here and take a look at what is going on. There's not much to see here, so we'll just take a look at the state of the ports, show PTP interface. And you see that port 1 is a clock source. So this is the one pointing to the Ixia ordinary clock. In interface 5 is the clock sync. So this is the one that is connecting us to the grant source. Now, we also see that this has been added. Peer-to-peer mechanism is being shown here as the delay mechanism. And we also see that the mean path delay here is 26, and for the uplink, and a lot larger for the downlink, which makes sense because we do have a transparent clock in between. So, and you see that a number is pretty stable there. The mean path delay is pretty stable. In this case, we don't have other traffic running, so that makes sense. So now you see that this is being auto-refreshed, and we now have the slave clock or the ordinary clock here. And here we see the offset going up and down, the maximum offset of 77 nanoseconds. This is pretty good. And then we have the minimum offset and also the path delay, etc. So we have all the details that we might want, and the numbers look and make sense here. So if we look at the statistics here, show PTP statistics. we see that the statistics are heavy on the path delay, the peer delay request responses. And you see here the presence of the follow-up messages. And if we decoded that message, if we expanded that message, we would see that this is the one that actually carries the timestamp for the correction of the offset calculation. Right, so that's all. Thank you.